Hi everyone, my name is Andreas Zuika and I'm evangelist for Epic Games. In this video, I will show you how to use the new full body eye key solver in Unreal Engine 5 to do a 100% procedurally animated character. After a short introduction into the solver used in Control Rig, I will show you how to build animations in several layers. If you want to learn more about Control Rig, check out our website where you can also find my very first steps. So the logic for the walk is currently done in Blueprint. We use full body eye key to pose the dragon only with using the foot locations. Leveraging a post-process animation blueprint, we can layer several secondary motions on top. We will dive a bit into physics for the tail and other dangly parts for the dragon, and we will end up with adding the ability to reach for nearby apples. So let's start with checking out the solver. Once you have enabled the Control Rig plugin, you can create one by making a right click on the skeletal mesh, which I have already done here. Here we have a simple starfish-like character that has 5 limbs with 4 bones for each limb. By enabling the display axis on selection, you can see your bone orientation. For this demo, I colored the mesh for better understanding of the bone axes. To find the full body eye key node, you have to enable the plugin. Here, we have different settings. We can define the root of the chain. We have effectors, bone settings, and settings for the solver, and a little bit of debug. For this starfish, the root of the chain is the center bone. Next, we need effectors. Let's start with the left arm. I already created some controls for each tip of the limb. Just plug in the transform, and we can see it is already doing something. Next, we need to set up all controls. I have prepared that here. Let's see what we got. So the solver is already doing a pretty good job, and we can get pretty nice poses by just placing around the controls we plugged in. And when we move the center, it's doing this. Now to the general settings. High iteration increases CPU cost. The mass multiplier affects bone resistance, and here we can enable stretch. You can also pin the root bone translation. Let's take a look at the settings for the effectors. With offset alpha, you weight the ability for the bone to reach the target control. So with 0, the effector remains in input pose. And strength affects how much this effector influences the whole eye keychain. And now let's take a look at the bone settings. Let's zoom in one of the arms. Let's go here and take a look at this bone. When we move this around here, let's disable stretching for a second. You can see the second bone in the chain doesn't really know what to do. Let's fix that. So we add a new bone setting and define which bone we want to influence. First, there's rotation stiffness. Setting it to 1 will completely lock the bone rotation. The position stiffness is doing the same, but for the location. And then we can lock each axis. For example, when we lock Z, now it keeps its orientation. And what we also can do is we can limit it to, for example, between -45 and 45. And then we have this. So, but let's set him free again. A very helpful setting is the preferred angle. When we set this on the Z-axis, we specify how much the bone should rotate when the chain is squashed. Sometimes it helps to set the duration to 0 because the preferred angle is done first. In this way, we can directly see the result of our settings. And by setting it to a negative value, the rotation is in the other direction. So in this way, we can set up the rules how our bones should behave. So the solver is doing already the heavy work you would normally do with quite a complex rig. With this knowledge, let's now dive and take a look at our character. This is a blue dragon. He has 2 feet, a head with big eyes and a tongue, and he has wings, some tiny arms, and a pretty long tail. One of the most important things I learned in this project is splitting up your animation in different pieces. So for him, we will have first a control rig with a full body eye key for the base pose. And then we will have some animation blueprint that contains this control rig. We will have physics for the tail. And another control rig that drives the rotation of our spine. Then we will have some floppy wings, again done with physics, and a third physic asset for the tongue and for a little bit resisting hands. And then for the big eyes, we have some control rig that does some random eye blinking and eye movement. And in the end, we will have a post-process animation blueprint where we mix this all together. The post-process animation blueprint has some great advantages, and you can add it here to a skeletal mesh. And once it's loaded, you can actually enable it in all the viewports, which is super handy, and I will show in different occasions. This very modular setup has some great advantages. It is easier for debugging, testing, and tweaking, and it also gives us freedom how you assemble it. It can also be used for scalability and optimization. So with all this in mind and the full body eye key we just looked at, let's take a look at the setup for the base pose. So for the very first step, let's take a mesh that has boxes for each bone colored in the axis. So here is a full body eye key solver with the controls for the feet and for the head. Without any additional tweaking, this is what we already got. I'm using a very handy node here called Project to Parent, which allows me to parent controls dynamically outside of the hierarchy. So the football here will be parented to my foot control. The reason I'm doing this is to have the foot control at the position where later my trace for the automatic foot placement will be, and my bow will follow along. This is generating already pretty great results. So we can imagine how this would feel like when he's walking. One of the problems of an auto walk is very often they feel very without weight because the pelvis here is not moving. Let's fix that. So here I have some additional graph I made. So now if I move the feet, you can see his pelvis is coming around and have a little bit of a simulation. Let's take a look at how this is done. So basically we take the Z component of the both controls, multiply, add them up, and use a Verlet simulation with some settings. So now the pelvis is offset and is following along. When we now offset his head a little bit, then we get a pretty nice result and a dynamic movement. So now he would be ready to be animated in Engine. So I could use this control rig now and just drop it in a level and begin to animate. But as I started my journey in rigging and animating only a year ago, I lack good animation skills. I wanted to try how far I can get with procedural animation, so now let's try to hook this control rig up with a character and add some logic for the foot placement. The character here is based on the character class that comes with the engine. It has a skeletal mesh and a movement component. To drive the controls we just made, we need a left and right foot location. So I made two components. One is a leg and one is a leg manager. So the leg manager has not much in it. So basically it knows about all the legs. It updates the legs each tick, and it has a handy function so the foot can ask if at least one foot is placed so we don't end up with all feet in midair. So that's basically it. Let's take a look on the leg. So the leg manager is updating them and they're doing 3 steps. It's getting a target location, it checks for replant, and it takes a footstep. So last time I made an automatic walk, I got a lot of questions how this works. So let's go a little bit deeper here. The target location is basically taking array start and array trace end. That depends on the leg position. And then we have a macro here that's just doing the line trace. And if that fails, we do the line trace again, but this time with a longer array. And if that even fails, we fall back to our last target location. So then we check for foot plant. So if this target location has a certain distance to our foot position, then we say we want to try to do a replanting. So now the leg manager comes in handy. We can ask if this is okay. So if this is okay, we begin doing our replant. So we are not planted anymore, and we save the plant start position. We also say that the time since unplanted is 0 now. So now we take a footstep. So the footstep First, we calculate a percentage how much we have done, and then we use this percentage to lerp between the plant start location and the target location. And here we use curve asset. So here's the curve. We can tweak this later and give it more character for an ease in and ease out or whatever we want to do. So, but now we are just lerping between those both positions, and we need a Z component. So the food is really lifting from the ground. We use another curve here, which looks like that. And then we add this Z component. And now we have finally our food position, which should drive our full body IK and thus our whole animation. And at the end, we're just checking if the replant is done. So let's take a look how that looks like. So here are some debug nodes. The red one is our trace, the blue one is our food position, and the pink one is our last plant location. So this is looking pretty good. With this done, we now have to feed this data into our control rig, and we use an animation blueprint of the character here. So what this does in event graph is checking the leg manager, getting the legs, and then we save the left and right foot in this moment. And then in animation graph, this is pretty simple. We have only a control rig, and we're feeding in the left and right foot position we just calculated. So let's take a look on that control rig. It's basically the same as what we have done before. So we have our full body IK node with this both project to parent nodes. And then here we take the food location, and now we have to drive the controls. And in Unreal Engine 5, control rig has functions, which is super handy. So here we have a function that's taking the location. We transfer that from world, so to have it in our global rig space. And then we do another trace. And with this trace, if we hit something, we take the normal, using an aim mass with Z upwards. So that gives us a rotation. And now with the location coming in from the logic and having the rotation here, we now have a slope warp where the feet is placed on the surface properly. So let's take a look how this now looks like with the character. So first, let's add a character to our mesh here. And now let's see how this looks. So this is pretty convincing already without us doing any additional thing, but we see two problems here. First, his chin is really easily sticking into the ground, and our verlet for the pelvis is gone. So let's fix that. In the control rig, I made a new function that's called process pelvis. So let's hook this in and take a look inside. So what this is here is our verlet and the movement of the pelvis. So we have our weight back. And now we actually want to rotate the pelvis depending if he's moving upward or downward. So the chin is not sticking into the ground. Here I have a really handy debug. With Visual Debug, you can, in nearly all nodes, have an add Visual Debug, and this gives me the quad so we can see this. And here from Euler, we make a quad. So if I move this, if I put a minus here or a positive here, we are rotating the pelvis. So this is how we can actually manipulate him. And now the question is, where do we get this value from? So in my case, what I did is I do a trace from the head downwards. And depending on the distance between this and my former location, I can map this to some values. And that's what I did here. So now when we take a look, he has back his weight on his hip and it's moving upwards and downwards. And when he's moving upwards, he is rotating the pelvis a bit, which gives us this result. We have all these debug nodes, and it's really handy that you can use a.animnode.controlrig.debug1, and then it is displaying now our debug nodes, which is very practical when you want to see if what you try to do there is also happening out in the real world. But full body IK is not the only feature of the engine, and during this project, I learned about a post-process animation blueprint. So on a skeletal mesh, you can add a post animation blueprint that's based on the same skeleton. So I made that, and once you made that, you have in all viewports in the engine, you can enable it. And you see here's already stuff going on with his tail, his wings, and his eyes moving. So let's take a look. The animation blueprint here is doing several things. It looks like a lot, but if we take a look at the single pieces, it's actually pretty easy. So we get the input pose. In this case, our base pose, the full body IK had provided, and this is operating on top of that. So first we take that pose, and I have a rigid body node with a tail setup in physics. I will show that in a second. Then we cache this pose, and then we use this cached pose and have another control rig here, which is doing some spine movements I will also show later. And then we mix this with the incoming physics and blend them by bone on the tail and over spine. And this cached spline adjustment we use then to drive physics for the wings. We cache that, and then we have another one with physics for the tongue and for the hands. And last but not least, we have one control rig that is doing the random eye blinking. So that's basically it. The beauty of this is now we have all the single pieces. So in the moment I only want to check out one thing, I can bypass everything and debug really easy. Another big advantage is I can use this kind of setup when I'm limited on animation budget and blend in and out stuff depending on platform or maybe on distance. With this overview now done, let's take a look at different pieces, and I would like to show you a little bit about the tail physics. During this project, I learned some nice tricks setting up the physics, and I want to take the opportunity to show them to you as they might help you with your project. This tail consists of 8 bones, and I used the body creation tool to get some capsules and my basic setup. Then I went into the details of each capsule and cleaned up the data a bit. So I zeroed out Y and Z for the location and the roll and the jaw for the rotation. Let's get now to the physics itself. I set the linear damping to 1, and I wanted to have the tail to have some resistance to movement, so I set the angular damping to 120. Starting with 30 gave me a very good start and helped me out to find my proper value. So in the past, when I worked with physics, I had always one of those problems that this tail was on the ground. So let's boost up the gravity for a second and blast simulation so you can see what I mean. So that's what I normally got with all my setups. So let's set this back. So what's happening here is this is a chain, and the physics is pulling on the parents of the chain. So I have to do certain setups. So first of all, in the past, I went to the constraint, and then I usually bumped up the motor a lot. And that gives you jittering and a lot of other problems. So to counter that, I can actually manipulate the center of mass. So in this case, I move the mass up the chain back closer to the constraint, which makes it much easier for the physics to deal with this. And next, a good rule of thumb is to make the children half the weight of the parent. So here you can see if you go down this chain, I decrease the weight. And then I have a pretty okayish motor, which is pointing a bit upwards. And with this setup, I have this now. And this is exactly what I wanted. And no jittering, and it's fluid, and it's doing what I want. So this is perfect. So now I have a rigid body node in the animation graph. So here I add the asset. And the next thing I have to do is changing the linear and velocity scale on all 3 axes. Tuning this made a big difference once the dragon stomped around in the world. So if we now bypass everything and only take a look at the physics of the tail together with what we have done before, this is what we get. Pretty cool. So with this tail doing its work together with the base pose coming from the full body eye key, next what we want to do is taking a look at the wings, the eyes, the arms, and the tongue. But before we do that, we take a look at the spine, because the spine you can see here is moving a little bit unnatural. So when he's rotating left or right, it's staying stiff, and the tail is not following him and the head is not looking in the direction. Let's take a look how we can fix this. So with the physics on the tail done now, we can use this as an input pose to a new control rig. So now we need to know in which direction to lean. So I have this little function here that's taking the current and the previous rotation of the character, doing a delta between that, interpolated, and then we have a value which we can feed into our small control rig, because we can mix different control rigs together. So this control rig is only doing the spine movement. So when I now adjust the incoming value, you can see this is what we get. So let's take a look how this is done. First, I clamp the value between -1 and 1 just to be sure. And then we have to take a look at the hierarchy. So first the tail is going in this direction after the pelvis, and the spine is going in the other direction. So we do 2 iterations, one over the tail bones. So what we're doing here, we're taking the lean amount, multiplying that with the value for our rotation in Z, and multiply this quaternary with the incoming bone rotation. And then we use a weight. So the for loop has a ratio, which has the value between 0 and 1. We evaluate over a curve, and that is what we use as a weight. And that gives us the opportunity to model how this curve looks like. And then we do nearly the same for the spine up to the neck. In this case, we are using an interpolation node, which gives us the opportunity to have different values for interpolating between decreasing and increasing values, which gives us a nice head movement. So when he is looking left or right. So and this is a really, really small piece. And when we have this now all together, we can bypass the rest and take a look how this looks like on our small clearing here. So this is pretty awesome. This was a moment in the project where I was super, super happy, because now the tail movement has physics and we have control over his lean, and we can blend this together, and this looks really like a character, vivid and full. So yeah, with this done, now let's take a look at all the other parts, because basically we have talked about the basic setup. So we have another physics asset here for the wings. So that's following the same kind of rules. It's a little bit more floppy, like that. And then I have a third one, which is here, and that has all the rest. So in my case, this has the arms and the tongue. So the tongue is like that, and the arms are a little bit resisting. So yeah, like you would expect from this kind of dragon. So we just mix this in, and with similar settings we have seen before with a tail. And then last but not least, he had really big eyes. So I had to do something with the eyes because he was a bit lifeless without doing anything with the eyes. So here see is blinking. And when we take a look in the control rig, I am here using some randomness and accumulate time and a sinus curve. So it's not perfect, but it's doing its job for now. So that's what I do for the blinking, and for the eye movement, I have something similar on 2 different axes. So after a certain time, it looks like he's looking in another direction. It is not, as I said, it is not absolutely perfect, but for me, that was pretty nice proof how you can separate all that pieces. And this is how it looks all together now. So his tongue moving, his wings moving, his tail following him, he's blinking, and it looks like he looks out for stuff. And with this modular setup, we can use all the pieces in different areas. For example, we could use the control rig for the eyes even when we animate him in engine. That's pretty nice. So now let's come to an important topic. It is well known that blue dragons love red apples, which gives us an opportunity to show how the full body IK solver can work to reach positions in the world. Let's go first back to our very first control rig we made, because I want to show something with the animation blueprint. As you can enable it in all the viewports, we can also do it here in the control rig editor. And if I do so and add a little bit of a jaw control, you can see his tongue and all this physics is working on top of what I'm doing here. This is pretty nice. So in this moment, when I did that, I got the feeling I have a little creature on my computer which I'm playing with, instead of a convoluted, complicated character setup that's hard to work with. So this was really, really fun and something that gave me quite some joy. So when we want to take a look at the apple, let's assume this is the apple, and when I move it around, we want to look at this direction, so we can use an aim node. So the location of this, we can take as a target, and if you are like me, sometimes having trouble with the aim mass, it's a very good trick to first zero out the secondary axis, and then focus on what is the proper axis for your primary ones. So once we have that, the rest is a piece of cake. We have a transform and we can use this. In this case, I'm not directly putting it onto the control, which you would expect, but to a space. And the control is within the space, which gives me now the opportunity to animate on top. So I have now an aim, and I can do some adjustments, which now goes into the full body IK. That's it. So this is what we now need to do. And let's take a look at the control rig we are using for him. So here's the aim node, and here we have the rotation, which we feed into the control for the head. We can also take the world position of the apple, transfer it from world, and then interpolate the head between that, so he's reaching in that direction. So if we do so, we need the apple position. So the apple itself, here it is. We have a sphere, and when the player enters the sphere, we're calling a function that's on the dragon. So the dragon has this function. It's not doing much. It's actually saving the position of the apple, saying we are looking at it. And then we're using the animation blueprint to feed this into the control rig. So this is what we got. It is pretty close, but it has one issue, as you will see in a second. So he's looking at it, but he is actually not stopping looking at it, even if this is really hurtful. So how do we fix this? To explain a bit what we need to do, I made a small control rig to explain that. So imagine that there's a green line here is our dragon's direction, and the box is where the apple is. So depending on the distance, we want to decide if we want to take a look at the apple or not. And that's easy. We can just calculate the distance between both points, do a remap between 1 and 0, and then I'm using this to change the color of this line. So when it's getting red, we don't want to look at it anymore. So that's already good for the distance, but not for the angle. So how do we do that when we look to the back? And we can use a dot product for that. So in this case, the forward axis here is y, so that's what we use there. And then we normalize our direction. And if we now feed this into our color thing and set this to 0, then when it's blue, when it's in this direction, on particular it is 0, and on the back it's turning red because it's negative. So in our case, we put 0.5, which is in this direction, and that gives us a result we want. So this is all okay for bending the neck. And if we now combine the distance and the dot product result, we now have a weight that depends if we look in the right direction and if it's not too far away. So this basic mass I have here in the control rig. So let's plug this back in. And then instead of having a convoluted graph, I made a function, which is here, which does the mass and using this weight. And then I do an accumulate lerp. So he is moving towards that target I'm giving him. And with this done, we now have a 100% procedural animated dragon who loves red apples. I personally like a lot when he's getting close to the apples that are in the tree, because that pose he's making looks like he's desperately trying to grab them with his tiny hands. So here is one of the use cases how you could use full body IK and how you can approach a very modular setup in Unreal Engine. Again, I learned a ton in this project and I have to thank some people.
Aaron Langmead for taking my ugly base mesh and making it a gorgeous cute dragon. Kieran, who's the engineer for Full Body IK, for his guidance and help with the logic for the autowalk. Jeremiah and Craig from the Control Rig team for being always so patient with all my questions. Special thanks to Charles Anderson, who taught me a lot about character physics. And last but not least, Jordan Walker for the awesome volumetric clouds I could use.
You can find more information about the animation features and Full Body IK on our website. Also check out the demo of the early access version of Unreal Engine 5, Valley of the Ancient, where the Ancient uses a lot of the techniques I have shown here. There's more to come. We are developing editors to make it easier to create Full Body IK setups, or the ability to create global functions in control rigs to share them between different rigs. As someone still new in this field, I'm very excited to see what developers out there will do with this. Thanks for watching and see you next time.